You know, for decades, every single electronic device you've ever touched has been built on one very simple idea: controlling the flow of an electron's charge. But what if I told you that's only half the story? It turns out every electron also has this other secret property, its spin, that could unlock a whole new technological revolution. Today, we're diving into Spintronics.
We've all heard of Moore's Law, right? This idea that our computers are constantly getting smaller, faster, and more powerful. Well, we're starting to hit a wall, a fundamental physical wall. Our transistors are now so ridiculously tiny that managing the power they need and the heat they pump out has become this massive, massive challenge. The old way of doing things? It's just about run out of steam. We need something new.
And that something new is spintronics. So instead of just using an electron's charge to represent a 1 or a 0, spintronics looks at this other, totally fundamental property, its spin. The easiest way to think about it is like this. Imagine every electron has its own tiny built-in compass needle that can either point up or down. In this new world, it's not the charge that carries the information, it's the direction of that spin.
Okay, so let's break this down. Old versus new. Conventional electronics, on the left, uses charge. It's like a light switch. You flip the power on, you have a 1. But what happens when you turn the power off? Poof, the information is gone. That's what we call volatile memory. Spintronics, on the other hand, uses spin, which is much more like a magnet. You can set its direction, up for 1, down for 0, and it just stays that way, even with the power completely off. And that right there, that non-volatility, is an absolute game changer.
So moving beyond charge isn't just some neat physics trick. What does this actually get us in the real world? Let's talk about the incredible promise of this technology.
The advantages here are, well, they're huge. We already talked about non-volatility. I mean, can you imagine a computer that boots up instantly because its memory never ever forgot a thing? On top of that, it promises way faster processing, it sips power instead of guzzling it, and it lets us pack things in even tighter without turning our devices into space heaters. It basically addresses every single problem our current tech is facing.
This whole field didn't just pop up overnight. It really all began with a single massive breakthrough that proved that we could actually control electron spin, that it wasn't just a theory. Let's get into the discovery that kicked the whole thing off.
So here's how it all went down. Back in 1988, scientists stumbled upon something called the giant magnetoresistive effect, or GMR. It was this wild discovery that you could dramatically change a material's electrical resistance just by changing the magnetic alignment of its layers. This led right to the first real spintronic device, the spin valve, and then, a few years later, its much more powerful successor, the magnetic tunnel junction, or MTJ.
So on the left, you can see the early spin valve, and on the right, the more advanced MTJ. They both work on the same basic idea. They've got these layers of magnetic material. When the magnetic direction of those layers are aligned, electrons with the right spin can just cruise right through. That's low resistance, R0. But when they're anti-aligned, it gets much harder for electrons to pass, creating high resistance, R1. The MTG on the right just uses a smarter design that makes that difference between high and low resistance way stronger.
And this chart really shows you why that MTJ was such a big deal. The first spin valves gave us maybe a 5 to 10% change in resistance, which is cool, but the signal isn't super clear. Then the MTJ comes along and delivers a whopping 20 to 50% change. That huge gap between the on and off states is what made the technology robust enough for the real world.
All right, so this isn't just lab stuff or ancient history. Spintronics has already quietly invaded the devices we use every single day. Let's look at where you can find it right now.
Seriously, if you've used a computer with a traditional hard disk drive in the last 20 years or so, then you've used Spintronics. The tiny little read heads that scan the disk to pull up your files, those are built with GMR spin valves. Their incredible sensitivity is what let us cram terabytes of data onto those spinning platters in the first place.
But hard drives were just the opening act. The next major revolution is something called MRAM, or magnetoresistive random access memory. And the dream here is to create what you might call a universal memory, something with the blazing speed of the RAM in your computer, but with the permanence of a hard drive.
And the advantages of MRAM are just stunning. It can write data 1,000 times faster than the flash memory you've got in an SSD or your phone. And you know how flash memory slowly wears out every time you write to it? MRAM doesn't do that. No wear out. It uses less power, and of course, it holds onto its data when you turn it off. This is the technology that could finally give us those truly instant-on devices we've all been waiting for.
So GMR and MRAM are fantastic, but they're still based on that very first breakthrough. To really unlock the full potential of spintronics, to go beyond just memory and into actually processing information, we need to invent entirely new kinds of materials.
And the holy grail, the thing researchers are desperately searching for, is a material called a half metal. So in a normal wire, electrons of both spins, up and down, just flow together. But in a half metal, it's like a perfect one-way street. Electrons with one spin, let's say spin up, flow through like it's a superhighway. But electrons with the opposite spin, they get completely blocked, like they hit a brick wall.
Now, why is this one-way street so important? Well, remember that 50% resistance change we got so excited about with MTJs? A device built with these perfect half metals could theoretically have a change of hundreds, maybe even thousands of percent. At that point, you've moved from a system with a high and low signal to a true perfect on-off switch, controlled entirely by magnetism.
And once you have a perfect switch like that, well, the possibilities just explode far beyond making better memory. You can start to reimagine the fundamental building blocks of computing itself.
This is where it gets really futuristic. We're talking about things like spin FETs, basically reinventing the transistor to use spin instead of charge, which could lead to entirely new kinds of processors. We could see spin LEDs for new displays, super fast optical switches, and maybe most profound of all, the unique quantum nature of spin makes it one of the best candidates we have for creating qubits, the very heart of a quantum computer.
You know, the potential here is so vast, so unknown, that the original researchers who kicked this all off put it perfectly in their paper. The most interesting devices will probably be those that we have not even contemplated here. This field is so new and so fundamental, we are almost certainly just scratching the surface.
So, we started with this idea that our current electronics are hitting a wall. What spintronics shows us is that there's a whole other dimension to play with. By moving beyond just charge and learning to control spin, we're not just improving our old tech, we are opening the door to something completely new, which really just leaves us with one final, huge question to think about. What really happens when we finally learn to harness the spin of every single electron?